Hey class, today we're going to continue on with section 4, which talks about entropy change in chemical reactions. So we tabulated the entropy change of a system in the last lesson. We used that by looking at the absolute entropy values found on the table that contained the standard entropy values. Here we did it for a chemical reaction, which counted as our system, and we calculated it using the following equation. Delta S, which is the change in entropy, equals the sum of the entropy values for your products minus the sum of your entropy values for your reactants. But how do we actually go about finding it for the surroundings? Well, the change in entropy of the surrounding is going to depend on how much heat is absorbed or given off by the system. And remember, heat is enthalpy. This brings about what we've kind of hit on already in the past, and it's going to combine a lot of pieces of information that we've learned. For example, an isothermal process. Iso means the same or constant. Thermal has to do with temp. So things that happen at a constant temperature, we have the following equation. The change in entropy equals Q of my system divided by T. We've seen something similar to this equation, where all we have to do is flip that Q value, and that gives me my surroundings because I'm switching around that heat. Also remember from past lessons that delta H can be substituted in for Q. This allows us to derive the following equation, and I'm going to go ahead and star it because this is the one you're going to be using on your homework. It's the negative of the delta H value that you'll find from the system divided by T. You might be wondering, well, how do I find that delta H value? So here that delta H value is calculated the same way we did last chapter. You're going to be using the delta H values on that thermodynamic help sheet than you would the delta S. Same concept, the sum of the products minus the sum of the reactants. One thing I want you to know is the N and the M value. Both of those come from the coefficients of a balanced chemical reaction. So you're going to have to take into account coefficients of a reaction as well. Also note that different than entropy, enthalpy values, if they're an element in its standard state, they're zero. So for example, if it's just sodium, which is typically a solid at room temperature, that would count as having a value of 0. What we would do is once we find this delta H, we would go ahead and we would plug it into that equation I had in the last slide. And that will help me determine my delta S of my surroundings. Let's kind of walk through an example so you can see this for yourself. Calculate the change in the standard entropy of the surroundings for the synthesis of ammonia from N2 to H2. Notice here that it says surroundings, and we're given my delta H value instead of delta S. Products always are going to be first. Reactants are always going to be subtracted from that. Here we have 2 times, and if you look over here for ammonia, NH3, the value is negative 46.19, minus my value for N2, which N2 is an element. It's in its standard form. It's typically a gas, yes. And if you look over here, you don't see it on the list. So that's going to be 0 plus 3 times. Once you look for your H2 value, it's not over here. That makes sense. It's an element. It's in its natural form of being a gas. So 3 times 0. So here, when you do 2 times negative 46.19, you're going to get negative 92.38 minus 0. So it's just going to be the following value. My units for that are going to be kilojoules per mole based on my units that I have up here. From there, we have to plug it into that second equation that we've learned. So that second equation that we learned is delta S of the surroundings is going to be equal to negative the delta H value divided by T. So here we have negative. My delta H value was negative 92.38 divided by T. Here, T needs to be in Kelvin, and I have it as 298 Kelvin. From there, you can go ahead and solve. Notice that you have a negative outside, a negative inside, so that becomes a positive value. So positive 92.38 divided by 298 gets me 0.31. This is where keeping track of your units is very, very important. Notice that on the top we had kilojoules per mole, and then on the bottom we had Kelvin. So entropy, which is your delta S, is always, we learned last video, is always going to be in the units joules per mole Kelvin. So in order to change kilojoules into joules, we need to times this number by 1,000. And when you times that number by 1,000, you get 310 joules per mole Kelvin as your answer. Here, I'm going to have you guys try this problem on your own, see what you guys come up with, and we're going to check your answer. So why don't you go do that now? Okay, so here we can see that we're finding it for the surroundings. So we need to use the equation, the delta S of the surroundings equals negative delta H divided by T. We need to find that negative delta H value first. So remember, we're going to use our equation and our delta H values up here. Reactants are always going to be first, products are always going to be second. So here we have 2 water. Notice that the state of matter is liquid water, so we have to go to H2O with an L. Do not mistake and put a gas. So the L value is going to be negative 285.8. We're going to subtract this from our reactants. Oxygen is an element in its standard form, so it's 0. Hydrogen is an element in its standard form, so 2 times 0 is going to be 0. So here, if you were going to find this, 2 times negative 285.8 gets you negative 571.6 right now, kilojoules per mole. This is my delta H value, so I have to go plug this into my equation. Negative, okay, my delta H is negative 571.6 divided by T. So here my T value is still 298, which it makes sense that it's 298 because it's about standard temperature. We want to keep it pretty constant. We have a negative times a negative, which becomes a positive. So positive 571.6 divided by 298 gets me 1.92 is what it rounds up to, kilojoules per mole Kelvin. Again, we want this in joules, so we're going to times it by 1,000 to get 1918.12 joules per mole Kelvin as your final answer. So that makes sense. If we're going to have water form, that we're going to have 1918 for our surroundings if you guys follow everything correctly. So how'd you guys do? So entropy in the universe and the second law of thermodynamics. Now remember, to find the delta S of your universe, it's just your system plus your surroundings. So if we look at those values that we had the last couple lessons, when we did this for the reaction of ammonia forming, our system was negative 198.3. Our surroundings was 310. And if you were to add those together, we're going to see that the universe actually comes out to be 112 joules per Kelvin. One thing to notice is that, hey, this is a positive value. because the entropy of the universe is always increasing. So again, since the delta S of the universe is positive for any spontaneous reaction, we also know that this reaction is spontaneous. If it was not spontaneous, the delta S of the universe would equal 0, and we didn't see that happen. So we know this is something that happens on Earth that can occur. So that's the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help.